So we're looking at the Gibbs free energy and delta G. We want to be able to calculate our delta G values here. And so we'll need a delta H in other methods. Calorimetry, etc., Hess's law. For our calculation for delta S, the easiest way we're going to calculate delta S is by using Appendix D data as well. Appendix D, the data tables. This is going to give us delta S standard for the reaction. And this is just the sum of nu S for the products, the absolute entropies, minus the sum of nu S for the reactants. One thing we have to keep in mind is typically the units for a delta H are in kilojoules per mole. The units for delta S are in joules per mole Kelvin. So we're working with smaller energy amounts. So we're going to have to convert. We either convert the joules into kilojoules or the kilojoules into joules.
What's the symbol in front of the S?
Delta.
No.
Oh, this one? Mu. Or nu, actually. Nu. Nu is the number of moles. This is going to be the easiest. But if we use Appendix D data, then we're restricted. What are we restricted to? What are the restrictions on Appendix D? Exactly. 1 bar and the restrictions you can just see. They just write it at the top of the table. Restrictions are going to be, oh no, don't do this. Okay, good. 298 Kelvin, or 298.15, depending on how precise you need to be. 1 bar. 1 bar and 1 atmosphere are close, They're 1.01325 bar in an atmosphere, so it's off by about 1%. Actually, this is exact. And one more restriction. What is it? 1 molar. So we're fine here, except this little symbol here. Let's go back. This little symbol here, does that indicate the temperature? No. And so we have to indicate the temperature. And so if we're using Appendix D, then the temperature is restricted to 298 Kelvin. If we're working at a temperature not at 298 Kelvin, then the data is not going to be accurate. And so we have to be careful with that. It may be close. And so these are our restrictions. And so if we were to calculate our delta G, probably the easiest way of calculating delta G is to calculate delta G under standard conditions at 298 Kelvin. If we do that, then we can use our delta H under standard conditions at 298 Kelvin. And then our T is going to be easy because T can only be 298 Kelvin. And our delta S naught we're going to get from this at 298 Kelvin. It's the easiest. And so this is delta G under standard conditions at 298 Kelvin. All right. There are ways to calculate. Oh, crap. All right, that didn't save. Okay. Unfortunately. Let me see. 41. Four minutes ago. So this is a pretty standard calculation. So we'll look at a reaction, and most of our reactions happen, let's say at room temperature. So an example of this kind of calculation would be, let's just look at the combustion of methane plus 2O2 gas. This is going to yield CO2 gas and 2 waters. Now, should the water be gas or liquid? The water should be gas. Normally, when you combust it, it's going to be a gas because it's so hot. But what we're going to do is, this is at 298 Kelvin, and I don't have the data at, let's say, 800 degrees C, 1,000 Kelvin or something like that, 1,100 Kelvin. I don't have that data. And so what I have to do is I have to wait. I have to wait until it condenses and cools back down to liquid, 298 Kelvin. So this is at 298 Kelvin. And so the temperature might skyrocket up, but I gotta wait until it comes back down to 298. And then I know because if it's still a hot mess of gases, eventually all that heat is gonna go to the surroundings, right? And so I need to know all that. I want to know the total heat dump into the surroundings. That heat could be used to do work, of course, or it could just be left as heat, because the change in enthalpy, well, we can relate that, our delta H. But anyway, the delta G is going to tell us the maximum amount of energy that's going to be available to do work in this particular reaction. And so that's one of the things we'll want to calculate. And so let's go ahead and calculate delta G naught at 298 Kelvin for this reaction here. And so the first thing is I want my delta H as a formation, because I'm going to calculate this. So I have to look up the delta H of formation of methane. What about O2? You should know the delta H of formation for O2. What is it?
0.
It's 0 kilojoules per mole. Delta H of formation of H2O I have in this table up here because it's hydrogen. And so delta H of formation of H2O liquid is different than the delta H of formation for H2O gas. And so we have to make sure we use the correct state here, which is going to be the liquid state at minus 285.8. So let me go down here. Minus 285.8. Oops, come on. Better save this. Units are going to be kilojoules per mole. I could put the units over here, and that way I don't have to write the units in the entire table. I'm just going to make a little table here. Let me save this so I don't lose this next time it crashes. I don't know, something is weird with this computer. Ever since it's been brand new, it's had this problem with Word. So I'm going to just open Appendix D here, see if I can get the chart up. So I just want to open another window with a textbook, but they used to allow this, and then they stopped, but hopefully they corrected that. So I'm going to open a second window. So for methane and CO2, we're going to look at carbon in Appendix D. Which is element number 6. So, oh, actually, this is alphabetical. So we'll just go to C. All right. Here I see CO2. So let's go ahead and write that. Minus 393.5. Okay, but I don't see methane. And you probably, or you may remember that these are all inorganics here. And they separate the inorganics from the organics. And so methane would be considered an organic. And the organics are at the end of the inorganics. And this is often done in data tables, like in what are the big reference? If I wanted a bigger table than Appendix D, where would I look? What book would I grab off the shelf, the library? You guys remember the names of it? No. I always remembered it because CRC, I always remembered what the CRC stands for, the acronym. Do you know what CRC stands for? And then I never forgot it. I learned it in Chem 4. CRC stands for the Chemical and Rubber Company. And so I always, well, nowadays I guess people just don't use it that much because of Wikipedia or whatnot, but I used to use this all the time, the CRC handbook. Everybody had a CRC handbook. In fact, I ended up buying one. It was like $200. But I got a special discount. If you go to the ACS meetings, they give you a really good discount on the CRC. So I have the old edition of this. This is updated every year, you know. And I think I have the 80-something edition, something like that. This is what it looks like. How much does it weigh? It weighs 6 pounds. It's just full of data tables. There's a lot of thermodynamic data in there. There's one more that's quite common. This is more biased towards inorganic compounds. There's one more that's more biased towards organic and biological compounds. What was that one called? It was the drug company. Anybody remember? Yeah, it's just, it was a brief mention in Chem 1A. I talked about it at that time, usually. It's the Merck index. Merck index is another good, handy reference source. Of course, they have the online version, but it costs money, so I haven't paid for it. Library probably has it, their subscription. You can go to the library. The library has physical copies of it too. There's one more that's quite popular. It's the Encyclopedia of Chemistry and Physics. So let's go back to this table and look for the organics. So you can see here inorganic substances, and now we have the organics. Organics are these hydrocarbon type based structures here. And so we have a lot of amines here, not a lot. We have methylamine, aniline, which is a ring structure. This is gas, aniline, liquid here. Alcohols here. These are ketones, acetone, carboxylic acids here. These are aldehydes here, acetaldehyde, formaldehyde. It has a little different structure, and these are hydrocarbons here. Yeah. And so methane, the simplest hydrocarbon, has a delta H formation of minus 74.81. Now, energy, is extensive. So we have kilojoules per mole. Well, we have 2 moles here, so we got to double that. And we have 2 moles here, so we double that, but that's 0. And so we can calculate our delta H. You've done this so many times. I'm not going to write the equation. Let's go ahead and just calculate it. 2 times 285.8 plus a 393.5. Okay, that's negative. Minus 74.81. So it's an exothermic reaction. It's quite exothermic at minus 890.29. That's highly favorable. Energy is going down. Units for this will be in kilojoules. All the moles cancel here. That's what the nu is, the moles. This is kilojoules for the reaction as written here, according to the coefficients there. Now we need to go to delta S. And so, but the way we get delta S is not by getting the delta S's, we get the S's. And so we're going to get the standard entropies, absolute entropies for these. So let's go take a look. How about this? O2, should it be 0? No, O2 is not 0. O2 is going to have an entropy, so we're going to have to look that up in the table as well. So let's get methane, since we're already here at methane. So the entropy here is 186.3. It's a gas, 186.3. This is a little lower than what I was saying, but it's close. 300 I said, but it's a bit lower than that. 186.3. It's methane. But the units here are different, and so let me save some work here. I'm going to write the units over here. This is going to be in joules per mole Kelvin. But let's go back to the others. So CO2's entropy is 213.7. 213.7. So CO2 has a little higher entropy. It's probably due to the vibrational modes, The methane has, you would expect it to be at a higher entropy. The reason I would expect methane to be at a higher entropy because it's got more atoms. And so when it's vibrating, there's more positions that the hydrogens can take during vibrations versus CO2. But CO2, it looks like this is something you can figure out quantum mechanically, the types of vibrations that are allowed for methane versus CO2, because looking at this, it looks like methane should have a higher, both are gases, so methane should have looks to be a higher entropy. But when we look at rotations, we've got vibrations, we've got rotations, we've got translations. Translations will be the same for both. But let's take a look at vibrations. As you recall, vibrations are quantized as well. And so these are called vibrational modes, the allowed vibrational energies for these. And so let's take a look at vibrational modes for CH4. Actually, maybe versus CO2. Let's see if it has both. No, this is from UCLA. And so the quantized vibrations here, this is what I was thinking, it would have more vibrational modes. It's going to have 1, 2, 3, 4 vibrations that are allowed by quantum mechanics. That's methane. Let's see the vibrational modes for CO2. This, unfortunately, is not animated, but it's showing by arrows. 3 vibrational modes for CO2. So when we're thinking about, this, there must be other things involved, in the determination of the absolute entropy. But very simply, if we had carbon monoxide versus carbon dioxide, that might be a more fair comparison. Which would have a higher entropy? Carbon monoxide at 298 Kelvin and 1 bar, or carbon dioxide at 298 Kelvin and 1 bar? Carbon dioxide. And indeed, carbon dioxide does. Let's take a look at if our prediction is correct. So, if we look at carbon monoxide's entropy, it's 197.7. If we look at carbon dioxide's entropy, it's 213.7. Now, why isn't methane higher? There's got to be additional reasons. It could be because of the hydrogen versus the oxygen. Hydrogen is just a simple atom. Whereas oxygen is going to have more electrons. But anyway, that shouldn't play a role, and unless these are all like positional type entropes. Anyway. But going back here, it's 213.7. We got that. We need the entropy for oxygen, and we need the entropy for water. Okay, so let's go ahead and get what comes next would be water. Now, liquid water's entropy is a lot lower. It's about 100 lower than gaseous water. Gaseous water is 232.7. Liquid water is 109.6.
I don't think that's water.
Oh, that's hydrogen peroxide. Hydrogen peroxide is going to be high. I was thinking that's a little high for water because water has kind of a lower entropy, right? Lower than expected. And so when we look at water's entropy, take a look at water's entropy. It's 69.91, in the region where solids are, the less ordered solids. And that's, what was the reason I said that it kind of has a lower entropy for liquid? Yeah, the hydrogen, the strong hydrogen bonding interactions. Whereas a typical liquid is going to have a little higher entropy. A little bit higher entropy. But anyway, if we take a look at liquid water, 69.91, gaseous water 180.8, which is a little low too. Compare that to CO2. It's a bit lower. And so what we want to do is, we don't memorize these numbers, but we just try to get a feel for the numbers by looking at them. This is part of the science, is just the observing part. Maybe we see some patterns. One guy who saw a pattern is Troughton. We'll talk about Troughton. Troughton came up with a rule that is called Troughton's law, but it really should be called Troughton's rule. But anyway, we'll come back to that later. And so let's go ahead and write this down. H2O liquid 69.91. And then we just need O2. So let's go get O2 from Appendix D. LMNO. Almost there. Here we could see the complexity go up. All three of gases, atomic oxygen, molecular oxygen, and ozone. And we can see the entropies here, 161 for atomic oxygen. There's no vibrations here, no rotations. It's only translational. And then we have O2, which is going to introduce vibrational and rotational, and O3, which is going to have more complex vibrations and rotation. So it's a little higher here. But O2 is 205.1, for the gas. So we do the same thing. It's extensive. So if we have 2 moles of O2, it's 410.2. 2 moles of water, we double that, 69.91. And so let's go ahead and calculate the entropy, delta S. This is under standard conditions. It's going to be absolute entropy of the products minus the absolute entropy of the reactants. And we have to remember that the entropies are extensive. All energies are extensive. So 69.91 times 2. Oh my gosh, 69.91. I have to bring the calculator in. Plus 213.7. Okay, that's the products minus the reactants. So minus 186.3. Minus 186.3 minus 2 times 205, or 410.2. And what did you predict? Did you predict the entropy goes up, down, or stays about the same in this reaction? And so the way we predicted is I expect the entropy to go down. Why?
Because we have basically three gases on the reactants and then one gas.
Yeah, one gas on the product and 2 liquids. And so it went down about 200. And so we got minus 242.98. And so that's kind of what we expected. The units here are going to be joules per mole. Actually, the moles are going to cancel out. Let me get rid of that. The units here are just going to be joules per Kelvin. Now, that doesn't mean you can't leave the moles in there. You could leave the moles in there. And so the typical units of delta H are kilojoules or kilojoules per mole. Typical units for delta S are joules per Kelvin or joules per mole Kelvin. You want to leave the moles in there. People will know what you're talking about. And so we can calculate our delta G naught at 290 Kelvin now. That's going to be our delta H, which was minus 890.29. Now, sig figs wise, I should have been keeping better track of this, but it's all right. Units here are kilojoules per, or just kilojoules. Just leave it. Okay, minus T delta S. So this is going to be minus T, which is 298 Kelvin, times delta S. Now delta S, I'm just going to convert this to kilojoules. And so I'll just move the decimal 3 over, 0.24298 kilojoules per Kelvin. Times 298. Plus 817. I get minus 817.88 kilojoules. Is that what you guys got?
Yeah.
Okay. This is the amount of energy this is the maximum amount of energy that you can use to do PV work, non-PV work. PV work is already compensated for in delta H, as you recall. Delta H factors in PV work. PV work is unavoidable if you do reactions at constant pressure. Okay, so that's the amount of energy. The amount of energy this is exothermic. And so this is the amount of energy the surroundings can use. This is the amount of energy the system loses and gives to the surroundings. Now, we have to recall that delta G is equal to minus T delta S of the universe. So what we want is we want a positive delta G. So if delta G is less than 0, that is it's negative, then delta S of the universe, because T is always positive, delta S of the universe has got to be greater than 0. So a delta G less than 0, we call this spontaneous. A delta G greater than 0 means that delta S of the universe is not going up. Delta S of the universe is actually going down. And we call this non-spontaneous. And if delta G is equal to 0, then we say that there's no driving force for change. This is just at equilibrium. So in other words, if we have a delta G that's less than 0, we expect the forward reaction to go. If we have a delta G greater than 0, that's going to favor the reverse. And if we have a delta G equal to 0, then it's at equilibrium. And so we have both the forward and the reverse, but no change is occurring. So this is quite useful, but we need to put numbers on delta G, like how big of a driving force is this? And it turns out this is a pretty big driving force, and we know it's a pretty big driving force because this reaction is so favorable. Combustion of methane is very favorable, and so this must be a very favorable delta G. We need some more delta G values to give us a better picture, so we'd like to take more observations so that we can see a pattern in the delta G values. What if we do delta G under standard conditions, but not at 298? What if we do delta G under standard conditions at some temperature T? If we do delta G under standard conditions at some temperature T, then we need delta H under standard conditions at that temperature. And we need to know the temperature, and we need the delta S under standard conditions at that particular temperature. These are not in Appendix D. So you're going to have to look for these. Delta H at some temperature T, and T's not at, let's say T is not 298 Kelvin. Now we're looking at this. Then delta H sub T and delta S at sub T, we have to find these or calculate these or determine these ourselves. This is the best method, but the easiest method is this. The easiest method is to sacrifice some accuracy. If we aren't doing an extreme, let's say we're still in the same phase, the easiest is to assume delta H, which is a function of temperature, does not change much. With T, and we assume that delta S does not change much with T. This is under standard conditions here. Therefore, delta H under standard conditions at temperature T is going to be approximately equal to delta H under standard conditions at 298 Kelvin. And delta S under standard conditions at temperature T will be approximately equal to delta S under standard conditions at 298 Kelvin here. So we'll do this. This only works, you know, if the phase doesn't change. So for example, if I say, okay, I'm going to apply that to this, but if I go above 373 Kelvin, what's going to happen above 373 Kelvin? Yeah, the liquid water is going to go to gaseous water, and then things are going to change quite a lot. And so as long as the phase, so if I don't go to, above 373, I keep the temperature kind of close to 298. Let's see. If I go below 273, what's going to happen? It's going to freeze. Liquid water is going to freeze. And so I have a limited temperature range that I'm going to look at. But let's say, what do you think was going to happen to the driving force if I increase the temperature? If I increase the temperature, do you think the driving force is going to get stronger or weaker? Now this is very tricky because oftentimes we increase the temperature and it looks like the driving force is getting stronger, but what's happening is the reaction is just getting faster. It's getting faster because the collisions are more violent and more frequent. And so that's kinetics. And so when we want to understand the reactions, we got to look both at the kinetics and the thermodynamics. We're just looking at the thermodynamic part here. And so we have to counter the effect of faster reactions in the way we perceive the reaction driving force. Because we might predict faster, and that's usually the case, faster reactions have a stronger driving force because there's more energy associated with it, and temperature isn't going to go up. So let's pick a simple temperature. Let's go to, like, say 325 Kelvin, or what should we do? 330 Kelvin, let's say. Let's say we do the same reaction at 330 Kelvin. Do we expect it to be a stronger or weaker driving force? And so we'll go to delta G. This is going to be under standard conditions, but the temperature now is going to be 330 Kelvin. And this is going to equal delta H. But is there a simple way to calculate delta H at other temperatures that you know of? Do you guys remember delta H? Did the book cover it? Let me open another window here, or let me go back to my other window here, and we'll take a look at this here. So enthalpies. I don't see it here. So let's go back here to our thing. And so what we're going to do is, this is not going to be totally accurate, but what we'll do is we're going to assume, this one we needed the value of 330 Kelvin minus T, which is going to be 330 Kelvin, to delta S naught at 330 Kelvin. And what we're going to do is we're going to assume that this is going to be kind of close to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. And so all we're going to do is we're just going to change the temperature here. And so this is our delta H naught. What did we just calculate up here? Minus 890.29. Minus 890.29 kilojoules. And our T is going to be minus 330 Kelvin times our delta S, which was minus 0.2, was about 200. So it was 242.98. Kilojoules. And so I'm going to get 330 times 0.24298. Minus 890.29. Minus 810.106 kilojoules. So did the driving force increase or decrease? What was it before? 817, minus 817, and now we're at minus 810. Did a driving force get weaker or stronger? It got weaker. And so this is weaker. It got weaker. And I didn't have to do the calculation. I could have told you it was going to get weaker. And you should be able to do this too. The way we do this is, it's very simple, like this. Let me just show you how to determine it. The way we do that is delta H favorable or unfavorable? This is favorable. How about delta S? Is delta S favorable or unfavorable? It's unfavorable. And we have a weighting factor T here. If I make T bigger, overall, it's going to make the whole thing less favorable, more unfavorable. And so if I increase T, it means delta S increases in importance, right? And it becomes increasingly unfavorable. So increase T, I'm going to increase the unfavorability of this. If I decrease T, then I'm going to decrease the unfavorability of this because, it's going to mean that S is going to be less in terms of magnitude on the overall equation. Does that make sense? And so we could do this quite simply here. In general, we have delta H. Actually, delta G is equal to delta H minus T delta S. And so let's look at some scenarios here. If delta H is negative and delta S is positive, then this is always favorable. It doesn't matter what the temperature is. And so we say that this is spontaneous at all temperature. All temperatures. If the delta H is positive and delta S is negative, then it doesn't matter. This is unfavorable under all conditions. So this is non-spontaneous at all temperatures. However, in the last scenario, we have this is a negative and this is negative. So what we say here is this is non-spontaneous at low temperature. Or no, sorry. Non-spontaneous at, not low temperature, at high temperature. And let's say I have this scenario. This is positive, but this is positive. And so the entropy is favorable, but the enthalpy is not. We can make this spontaneous. This is going to be I should say this. Non-spontaneous at high temperature, spontaneous at low temperature. This one is going to be spontaneous at high temperature, non-spontaneous at low temperature. Let's do two quick examples of this, and we're going to adjust the temperature to see at what temperature does this switch over. So we know that the combustion of methane is spontaneous. The question is there a temperature where it would go from spontaneous to non-spontaneous? So is there a temperature where it would transition to non-spontaneous? All right, yeah, there is a temperature, and we can see it here. You know, our delta G naught is minus 817. You know, kilojoules at 298 Kelvin, and so that's spontaneous. However, if we change the temperature, it's going to change things. So we'll just do delta G naught here, and we're looking for the temperature T. And we have a delta H. Our delta H is minus, what is our delta H? Minus 890.29. So this is our delta H. This is minus 890.29. That's favorable. Negative delta G is favorable. This is kilojoules. This is going to be minus T delta S. Delta S is minus 2.24298. It's 24298 kilojoules. So it's very simple. If I want the temperature, all I have to do is I have to cancel out this negative. How do I cancel out that negative? I make this positive. If I can make this positive 890.29, then I'm at 0. So all I have to do is get a temperature greater than this to make this number bigger. So if I just make this a little bit bigger than 890.29, then this whole thing is going to go positive, and it's going to be non-spontaneous. So this is where it transitions. And so what is that temperature? And so in other words, what I want to do is at the transition, it's going to go to 0. And so what I'm going to do is I'm going to set this to 0 so that the positive entropy term cancel out the negative enthalpy term. So we set that to 0. And then we solve for T. So solving this for T, T is going to equal minus 890.29 kilojoules divided by, okay, so I add that to both sides. This is a positive, so this is going to be negative. So this is going to be negative 0.24298 kilojoules. Kilojoules cancel. This is kilojoules per Kelvin. I flip the Kelvin over, and what's that temperature? So it's going to be 890.29 divided by 0.24298. That's 3,664 Kelvin. And so we want a temperature greater than 3,664 Kelvin, minus 273. Or 3,391 degrees C. 3,000 degrees C. Is that a very feasible temperature? No. this doesn't seem, this is very high temperature. So it doesn't really seem feasible. I'll just say not feasible. But in theory, it seems okay, right? In theory. Let's do another example. Let's look at a non-spontaneous reaction here. H2O liquid goes to H2O gas. Let's look at delta H for this. Is it positive or negative? To vaporize water, do you have to add energy or do you have to remove energy? We have to add energy. It's endothermic. And then delta S? It increases. Yeah. So this would be, this is not favorable. So this is unfavorable. However, this is favorable. So what we say is this is going to be spontaneous at high temperature or low temperature? At high temperature. And so at 290 Kelvin, does H2O liquid boil, essentially? At 290 Kelvin, spontaneously boil to gas? No. And so let's go ahead and take a look at the data for this.
Why does delta S? Why is delta S like increasing favorable? Because wouldn't increasing the entropy of the system like lower the entropy of the surroundings?
So entropy is kind of weird. You know, because it doesn't follow along like the first law of thermodynamics in that sense. And so the first law of thermodynamics is energy is conserved. And so it's a zero-sum game. So like if somebody loses, then somebody must have gained. And vice versa. The entropy, no, entropy has to, entropy of the universe is always increasing. If the entropy stopped increasing, then nothing would happen. We'd be done. Basically, the entropy would, and so we don't do delta S of the system is equal to negative delta S of the surroundings. That doesn't quite apply in this. But the entropy, we got to think in terms of, you know, how, you know, because how does that impact the entropy of the surroundings? And so that we aren't even factoring that in. The only thing that is considering the surroundings is delta H because of the PV work, but the entropy is not. We're just looking at the system, so the surroundings can be doing anything. And so strictly system here. Here, the energy entropy, what I talked about earlier, depends on the surroundings because we got to dump the energy into the surroundings and increase the entropy of the surroundings that way. And so here, the entropy of the surroundings will increase. Actually, if this is endothermic, the entropy of the surroundings must be decreasing in order for the enthalpy to increase. Does that make sense?
How does that not violate the thermodynamics? It's because like the net entropy is still increasing, like in the system.
Yeah, the delta S of the universe is increasing. And so here, yeah, the net entropy of the whole thing is increasing. However, we could have scenarios where the delta G is unfavorable. And so the net entropy of the system, including energy and positional entropy, are actually decreasing. You know, things are getting more ordered, and it's costing energy to do that. And overall, then, that means the entropy of the surroundings must have increased to compensate for that. And we have to look at that somehow. But here, we'll just, at least for this term is only system. And so we're looking at how the entropy of this, you know, here we'll have water molecules packed together in a liquid state versus water molecules in the gaseous state. In the gaseous state, there are much fewer constraints. In the liquid, it's constrained. All the water molecules must be stuck to one another. Here in the gaseous, we don't have that constraint, and they can move about. So there's a lot more freedom here. And this is all we're looking at in this term. This is our delta S of the system.
So for the delta G equation, why would the delta S be unfavorable and the delta H be favorable in that case? Like when we were calculating the that increasing the T.
Because it depends on how much. Okay, the delta H term, if you want to talk in terms of entropy, then this one is unfavorable. Let's go back to this one. This one's unfavorable because the entropy is actually decreasing of the system. But this is more than compensated for by the increase in entropy of the surroundings, because this is going to be a huge heat dump into the surroundings. And all that heat is just going to go into, you know, we're converting this chemical potential. And so, in other words, we have chemical potential energy being converted into heat. And so that's going to be a huge increase in the entropy, which wasn't there before. And so this is the entropy of the surroundings that are going up, and this entropy of the surroundings is going to overcome the unfavorable entropy of the system here. Okay. And so this is how that works. But overall, if we want a spontaneous process, the entropy has to increase, and the entropy, there's no fixed limit to the entropy. The entropy has to continue to increase for things to change. If the entropy does not increase anymore, then there's no change, there's no driving force for change, and nothing will change. They say at that point, you know, all the matter in the universe is going to be scattered and distributed.
So it's basically like the delta H, as it dumps enough heat, it's like overcomes the loss of entropy. Yes,
exactly. Yeah, that heat dump is going to be a massive increase in the entropy of the surroundings. So anyway, going back to this, we can change the degree of favorability or unfavorability by changing the temperature on the entropy term. We can't do anything on the enthalpy term, that's fixed. And so what we're going to do is we're going to just take a look at this at 298 Kelvin. So we'll go ahead and calculate delta G naught at 298 Kelvin, which is going to equal delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. Now, for H2O liquid, let's go to the table and take a look at the values here. Actually, I guess I had the values up there earlier. I just didn't have H2O gas. So H2O liquid is minus 285.8 for the delta H. So let me write that here. delta H is in kilojoules per mole. And H2O gas, is minus 241.8. It's 241.8. Okay, and then let's look, this is under standard conditions, and these are under 298 Kelvin. And then we have the absolute entropy at 298 Kelvin. For H2O liquid, the absolute entropy is 6991. And for H2O gas, the numbers earlier, H2O gas, 188.8. And so we'll just plug in the numbers here. This is going to be 44.0 kilojoules. This is delta H of vaporization at 298 minus 298 Kelvin times, this is going to be, what, 118? Let's see, 188.8 minus 69.91. $118.89. Now this is in joules per Kelvin. What I'm going to do is I'm going to convert that to kilojoules. Since kilojoules are the typical unit for delta G. So I'll just divide it by 1,000. Divided by 1,000 times 298. Is that minus 44. This is unfavorable. This comes out to positive 8.57 kilojoules. That's unfavorable. The reverse is favorable. So at 298 Kelvin, steam should condense into a liquid. The reverse is favorable. However, delta G is a function of temperature. Delta G changes dramatically with temperature. So dramatically, it can reverse the driving force. So what I'm going to do is I'm going to, the driving force is backwards here. I'm going to reverse it and make it go forward by changing temperature. So, I assume that delta H doesn't change much with temperature, and delta S doesn't change much with temperature, but delta G changes significantly with temperature. And so what we're going to do here is we're going to look at what temperature does it go spontaneous. So at what temperature will this go spontaneous? Well, not everything will go spontaneous. So for example, if it were plus minus, you know, it would never go spontaneous. Actually, you could calculate the temperature, but the temperature would make no sense. We can always calculate temperature. Sometimes I ask a person, you know, it just so happens to work here like this, but some people try to apply this to all scenarios. You know, and sometimes they get some ridiculous temperature like minus 350 Kelvin. Minus 350 Kelvin, it will switch. Is that possible? No, it's impossible temperature, so you have to have some knowledge. You can't just use the math equation and just punch it in. So let's try this then. So what we're going to do is we're going to try to cancel out the positive 8.57, or what? No, we're going to try to cancel out the positive 44 kilojoules by making it go negative. So this is going to be delta G at temperature T. This is going to equal our delta. It's going to be approximately equal to our delta H at 290 Kelvin. Right? We're going to just leave that because we don't have any of the numbers. Minus T delta S at 290 Kelvin. And so we know that this is 44.0 kilojoules. So we need to cancel that out. And so we need to cancel out that this whole term here, that is the T times the delta S at 298 Kelvin, which is 0.24298, I think, 0.24298, as I recall, kilojoules per Kelvin. We got to cancel that out by increasing this entropy term here. In other words, we're going to set this equal to 0. If we set this equal to 0, then the plus 44 has to be canceled out by minus 44. So this is where it's going to transition when delta G is equal to 0. That's going from, so currently we're going from positive to 0 to negative for our delta G. That's what we want. And so this is where it transitions. And so what is that temperature? So let's go ahead and solve for the temperature here. It's going to be 44 divided by 0.24298. And that comes out to 181. Is that right? Let me try that again. 44 divided by 0.24. 298.
I think you're using the old delta S, the first reaction.
Oh. Oh, that's right. I need to calculate new delta S. I was trying to be lazy, not do it. It's 118. That's right. 118.89. So this is going to be 0.18. Sorry. .11889. I was getting a weird number. So it's 44 divided by 0.11889. 370. So the temperature here is 370.08 Kelvin. Minus 273, 97.08 degrees C. The actual temp is 100 degrees C. Although this is in bar. What is the boiling point of water? I shouldn't do this. This is in atmospheres. What's the boiling point of water in bar? Do you know? Do you guys remember the Clausius-Clapeyron equation? A little bit? Clausius-Clapeyron equation, ring the bell? Clausius. Oh, maybe a Clapeyron. Clausius-Clapeyron equation from chapter 12. We can use this. I mean, let me just calculate, because our data is in bar and our boiling point is in atmosphere. So let me correct it. So what I'm going to do is I'm going to calculate the boiling point of water at 1 bar instead. And so Clausius-Clapeyron is ln of P2 over P1. This is the vapor pressure, is equal to minus delta H, vaporization over R, 1 over T2 minus 1 over T1. So I'm going to call T1 is going to be our delta H of vaporizations for bar 2. So T1 is going to be the normal boiling point, which is 100 degrees C. And P1 is going to be the vapor pressure at that, which is going to be 1.01325 bar. And then P2 is going to be 1 bar exactly. And we want to figure out what T2 is. So I know the boiling point at 1 atmosphere. This is 1 atmosphere. Vapor pressure. So let's go ahead and plug this in here. So I could either use bar or atmosphere. I'm going to use bar. So this is going to be 1 over 1.01325. Is equal to, my delta H, I just calculated it, is minus 44.0 kilojoules. My R, this is kilojoules per mole. My R, I'm just going to use 8.3145 joules per mole Kelvin. And so I could have gotten rid of the moles earlier, but I had to insert it in there. And then I have a conflict between kilojoules and joules. In the previous examples, I converted joules into kilojoules. In this one, I'm going to convert kilojoules into joules. One over T2, so that's 1 over T2 minus 1 over T1. 100 degrees C is 373 Kelvin. So let's go ahead and solve this for T2. So 1 divided by 1.01325. Take the natural log of that. Divided by 44, that would be 0.044. Divided by 0.044 joules times 8.3145. 8.3145 equals that. And then I'm going to add 373 inverted. So plus 373 invert. And then I'm going to invert it. Did I get the sign screwed up? Yes, I did. I screwed up my sign. Let me subtract 373 inverted. So the sign, it's positive. Did somebody calculate it? All right. Let me just do it one more time. I wasn't keeping track of the sign. 1325. Take the natural log of that, which comes out negative. And so this is the negative times the negative is going to be positive. So it's divided by, I'm going to times it by -1. I screwed up the sign. Divided by 44,000. 44,000 times 8.3145. 8.3145 equals. All right, then I'm going to add the inverted 373 plus 373 invert equals that, and then I'm going to invert my answer. And I get 372.6. I guess it didn't really change much, huh? 0.6. It should be 373, but a bar is a little bit smaller. So if a bar is a little bit smaller, it's going to boil at a little bit lower temperature, but not that much lower. So the actual is 372.65 minus 273. is 273. It's 99.6. So the boiling point of water at 1 bar is 99.65 degrees C. We're still off. My calculation was, I calculated 97 as my boiling point of water. Why are we still off? Yeah, because we made the assumption. What was the assumption that we made? Yeah. We really should use the delta H at whatever, 99.65, but that would, in order to do that, we'd have to know the answer before we even start the problem, so it doesn't quite, yeah. So what we say is it came out close. We didn't expect high accuracy. We just expected something close. And so we just say it's close. Not perfect agreement, but close. And so it gave us a decent answer. All right. Now, let's see. 3 minutes? Okay. What we want to know is this. We already talked about delta H, but what about delta H for other things? Other methods. Probably look at that, but what we're going to do is we're going to look at delta S. Appendix D is great for delta S calculations, but let's look at delta S other calcs. Now we looked at calculating S using the Boltzmann equation, but this is calculating delta S, and there's some thermodynamic equations that we can use to calculate delta S. Delta S is related to Q, and this reversible means there's some restrictions on how that heat is transferred. When you see this reversible, that means the heat is transferred in infinitesimally small amounts. In other words, it's transferred like infinitesimally slow. Something like transfer infinitely small amounts. Small amounts. And so there's some calculus involved in generating some of these relationships here. Calculus likes to work with these infinitely small bits of change. One of these is, actually, not all of these require calculus. Like, for example, this one, if we deal with a phase change, in a phase change, the temperature does not change. T is constant. And so in a phase change, we have something called delta H of the phase change. And so if we restrict the conditions, then Q is equal to delta H. And we can come up with this equation. And the equation that we come up with is delta S is equal to delta H of the phase change over the temperature of the phase change. So an example of this is, let's calculate delta S for water vaporizing from liquid to gas. We don't have that much time, do we? We could do that calculation later, but there are other equations here that we'll derive, but I'm out of time, so I'm going to stop here. So we'll probably finish this chapter up next time.